Okay, so we have two intersecting lines. We're going to be talking about two intersecting lines in 3 space. Now in 2 space, or just your XY axis, you guys would have gone over this concept in probably grade 10, maybe even grade 9, I think. In 3 space, the 3 same solutions still exist, where we have the option of 2 intersecting lines. So we'll try to do them in blue and red. So for instance, we have our red line and our blue line, which intersect with each other. Okay, we'll give it point A, we'll call it. So these two intersect with each other at point A, which we've already gone over examples like that in 2 space, and it's going to be very similar to solving it. There's also the case where the 2 lines overlap each other. Okay, we'll change that color to purple for this line. So this means that the 2 lines are actually on top of each other. So these are coincident lines. They have their same slope. And in 2 space, it used to be they had the same y-intercept. In this case, they're going to just cover all the same points. So in the first case, we have how many solutions? How many times do they cross each other? Just once. In our second case, how many solutions will we have? Infinite. We'll have an infinite number of solutions in our second case because they're right on top of each other. Our third case here, we're going to have the red line and the blue line will be parallel to each other. Okay? And if they're parallel to each other, how many solutions do we have in our third case? Anyone? No solutions in our third case. Okay? Now, this one only exists in 3 space, our fourth case here, and it's called skew lines. Okay? And skew lines are lines that do not cross each other, but are not parallel to each other either. Okay? It's a tougher concept if you haven't thought about it before. I'll try to draw a picture that almost represents it. I'm drawing on 2-dimensional object here, but think of it like this. We have 2 lines not parallel to each other, but think of the red one being almost underneath the blue one there. So our blue line is above and never coming down, and our red line is maybe below the blue line. Not parallel to each other, but they don't touch each other either. Okay? So we're going to have to figure out the differences between those. Algebraically, we'll have to prove, if we have no solutions, we'll have to prove either they are parallel to each other in 3 space, or they're skew lines that aren't parallel, but still don't have a solution, which will be a little something new for us to do. Okay? So the very first one we're going to go over is we're going to go over case number 1 here. We have 2 intersecting lines. So let's jump to another page. So our 2 intersecting lines, they've given us a line, call example 5. L1 is represented by this vector equation. Here is a point on the line. Here's our direction vector. And line 2 has our vector form of 1, 4, 6 plus t, -6, -1, and 6. Okay? So s and t in this case are a set of all real numbers. Okay. Now remember we had 4 cases. What we want to do is actually disprove 2 of them right off the bat. And the 2 cases we're going to try to disprove off the bat are what we called case 2 and 3, which were parallel and or coincident lines. Okay. Now we know coincident lines will also be parallel to each other. So that's the very first thing we're going to check for. Are these 2 lines parallel to each other? If they are they coincident? Okay. If they're not parallel, then we definitely don't have coincident lines either, and it disproves both cases. So we're going to look at our direction vector for both of these. Our direction vector is one direction vector. Can it be shown as a scalar of the other direction vector? So we're going to get rid of our scalars or parameters on the outside, and I'm going to just take the two of them to start. This one and this one here. And what we're going to do is we're going to set one equal to the other with a scalar in front. So can some scalar of k give us, this is our question, some scalar of the first direction vector give us our second direction vector? Okay. I want you to just quickly look, a fast way of proving this, and instead of putting variables to it all and distributing the k, will be just look at our x value. What do I have to multiply or divide the x value by to get the other direction vector's x value? 6. Okay? Let's try it. Can I multiply the y value by 6 and get -1? No. Right away, disprove it. Okay? Because I can't use that scalar, I should be able to use any scalar if they are actually parallel to each other. That scalar 6 doesn't work, which means these are not parallel lines. And if they're not parallel, they're not coincident. So we've disproved 2 of the cases already. The next thing we have to find out is, do they intersect each other? Okay? If they intersect each other, then we have 2 intersecting lines. If they don't, we have 2 skew lines in this case. So what we're going to do now is we're going to start to give some parameters to some of our questions here. Okay? We have, if we put these in parametric form, so line 1, we're going to put it in parametric form. So line 1's x is equal to -3 minus s, y is equal to 1 plus s, and z is equal to 4 plus 4s. Okay? Our line 2, I'm going to jump back up so we can see it. We're also going to put that in parametric form. Our x will be equal to 1 minus 6t, y will be equal to 4 minus t, and z will be equal to 6 plus 6t. Okay? Now that we have that, what these are saying, and we're going to find out here, is that this x value is equal to that, and this x value is equal to that. So in other words, if we're going to have a point of intersection between these two lines, this bracket can be set equal to this bracket, because x is, they're both representing just the variable x. I can do that for all 3 of these, that means. I only really need to do one of them in order to find out our parameter s, but I could choose any of them. I could set the y's equal to each other, or the 2 equations that are equal to y to each other, or the 2 that are representing z equal to each other. We'll start with just the x one since it's the first one. It doesn't technically matter. And the reason we do this is so we can find a value for our parameter s and t. Okay? We're going to try to solve what s and t can be. So, our very first equation, and we can set up all 3 just so you guys can see what it'll look like. 1 minus 6t is equal to -3 minus s. Equation 2, which would be our y's, is 1 plus s is equal to 4 minus t. And equation 3 would be 4 plus 4s is equal to 6 plus 6t. I now have 3 equations, 2 variables. Can I solve for my variables? Yeah, I can solve for my variables. I only really am going to need to solve for 1, but we'll solve for 2 just so we can prove what we're doing here. I'll take equation 1, and actually, just because I think it'll be easier, I'm going to take equation 2 and set it equal to s. In this case, what it'll do, it'll give me s is equal to 3 minus t. Okay? So now I have a value of s. I'm going to take that value of s and I'm going to plug it back into equation 1, substitution method here. Okay? You could use elimination. Nothing wrong with that. In fact, as we go on, they really get into using elimination in solving these in 3 space, but technically either work. So we take equation 1, 1 minus 6t is equal to -3 minus 3 minus t. Okay? This is going to give us 1 minus 6t is equal to -3 minus 3 plus t. We'll get all of our variables on one side, our constants on the other. When 3 minus 3 gives us -6, and I move it to the other side, it becomes positive. So 1 plus 6. And we're going to have t plus 6t. T is going to be equal to 7 in this case. Whoops, I lied. T is going to be equal to 1. That's 7t. T is equal to 1. Okay. So, with that one parameter we have, I can solve for my other parameter. And I'm going to plug it back into question 2, or equation 2. Equation 2 first stated 1 plus s is equal to 4 minus, our t value is 1. So this gives us 1 plus s equals 3. S is equal to 2. So we now have values for t and s. Now, technically, I should plug them both into equation 3 to make sure they're true. They should fall true, but we'll check. Equation 3, 4 plus 2. 4 times 2, and 6 plus 6 times 1 is just going to be 6. So we're going to have 12 is equal to 12. Great, they work. We got that information. Now that we have our two parameters, s and t, we're going to plug them into our parametric forms of the equation. Whoops, I went too high. Right here. We now have a value for s, and we have a value of t. When I plug those two in, we should get corresponding values. In other words, they should both give us the same point in 3 space, saying, and if they are the same point, that they cross at this point in 3 space. If they give me so, we're going to have our parametric forms of the equation. We're going to plug in our values of s. To make this easier, I know you guys can't do this, but I'm just going to copy and paste this down below. Oh, nuts. There we go. Okay, so we have our values. And I'm going to plug in my values for s and t into the equations. I know the highlights aren't quite matching right now, but you'll survive. So, line 1. X is equal to -3, and our s value is 2, so minus 2. X gives us -5 as a coordinate. Y equals 1 plus 2. Y gives us 3 as a coordinate. And z is equal to 4 plus 4 times 2. Z is equal to 12. So, the first line states that they should cross at -5, 3, and 12. We have to plug in our value of t into the other one to see if it gets the same values. This is going to prove it. Same values, that means they cross at that point. Not the same values, they are skew lines. They don't cross each other. So, line 2. X equals 1 minus 6. What was our value of t? 1? Yeah. So, minus 6. X is equal to -5. That one matched. Y is equal to 4 minus 1. Y is equal to 3. That one matched. And Z is equal to 6 plus 6. The reason I didn't write the variable t in because it was just 1. So it's just multiplying. 6 plus 6 is 12. Boom, they match. Okay. So because they match, that means they cross at the point 5, -5, 3, and 12. So these are intersecting lines we've just proven.